All right, so this is the 5C handout. So we'll just work our way through it. You probably learned at some point that in a triangle, the area is going to be 1/2 base times height. So if you have a triangle that looks kind of like this would be the height, and then this thing would be the base, right? And if you wanted the area, you just do 1/2 whatever number the base is times whatever number the height is. Okay, so let's say that you've got this triangle. Now, if it's on a graph, and the goal is to find the area of this TDL triangle right here, you could find the length of an altitude if you wanted to, but it turns out that none of the altitudes would be easy to figure out how long they are, because if you kind of think about it, here would be one altitude, but I don't know where it hits. Or here would be another altitude right here, but same problem, I don't know where it hits. Or here would be, let's see, how would this one look? From here, it would look kind of like that. But again, I'm not sure where it hits, and finding out where it hits takes a decent amount of work. But there's a way around it. So the way around it is actually to build this rectangle around the whole thing. So you're using slope triangles. And if you actually calculate how long these sides are of the slope triangles, we'll get a 9 here, a 3 here, a 7 here, 4 here, 5 here, and 10 down here. Okay, so there are the sides of our slope triangles. Now, in order to get the area of just this triangle in the middle, just that part, what we could do is actually find the area of the entire shape that I have, this big rectangle around it, and then subtract out the areas of this triangle, and this triangle. So I want to get rid of those 3 areas after I get the area of the big rectangle. So on the side here, I'll write find the area of the whole rectangle and subtract the areas of the 3 slope triangles. Now, the 3 slope triangles, these areas are easy to figure out, because if you look at this one right here, 3 and 9, if I flip it over, it looks like this, 3 here, 9 here. Well, 9 is the height, and 3 is the base, so I could just do 1/2 3 times 9. Right? Same deal goes with all of these slope triangles. So let's see the area of the rectangle. So it's 9 on one side and 10 on the other. So it's 9 times 10 equals 90. And then if I do, I'll number these triangles. So let's call this one triangle 1. I'll use Roman numerals here. So this one over here, I'll call triangle 2. Let me get rid of the blue. And then this one right here, we'll call triangle 3. So the area of triangle 1 is going to be 1/2 the base 3 times the height 9. So that's half of 27, which is 13.5. The area of triangle 2 is going to be 1/2 base times height. So that's 1/2, we could say 7 times 4, 4 times 7. Half of 28 is 14. And the area of triangle 3 is 1/2 10 times 5. Well, that's half of 50 is 25. And so if you look at the sum of the triangles, of the 3 outer triangles, that's 13.5 plus 14 plus 25. That's 52.5. So that means that the area of the triangle that's in the middle, TDL, is going to be the whole area, which was 90, minus these 3 areas on the outer parts. So it's 90 minus 52.5, which ends up being 37.5. Okay. So let's take a look at number 2. So that's just kind of a side idea, and it shows you how the slope triangles can be used for other stuff besides just slope or length there. Now we can use it for area too. Okay, so number 2, we've got ABCD is a parallelogram. Okay, so remember, since it's a parallelogram, right away we have 5 properties of parallelograms that are going to come in handy. So one of them is the definition, which says top and bottom and left and right would be parallel. We got another one that says opposite sides will be congruent. We got another one that says opposite angles will be congruent. We've got kind of the combo of the previous two, which says one pair of sides is both congruent and parallel. And then we've got the last one, which talks about the diagonals, which they bisect each other. Like that. Okay, so let's see. The goal, we know that the shape on the left is a parallelogram, and we know that angle A is the same as angle E. And the goal is to prove that AB is the same as CE. Okay, so before we jump into it, let's kind of look at what we can do with some of this stuff. Since this thing's a parallelogram, let's see. I know that these sides will be parallel. And if these sides are parallel, then I can link this angle to this one right here, because those guys will be corresponding angles. And then once I've linked D and E, I know that this triangle will be isosceles. So then I can link up these sides. And then since this thing's a parallelogram, I can link this side over here to this side over here. And then I can say AB and CE are the same size. So we're sort of going to use parallelogram properties to get from this angle to this angle over here. And then we'll use isosceles triangle and work our way back across the diagram. So let's see how this goes. Okay, so we'll list off the given first. ABCD is a parallelogram. It's given. And angle A is congruent to angle E is also given. Okay. So now let's use some of the parallelogram features. So let's do, like, I think we were going to use AB as parallel to CD here. So AB is parallel to CD. Okay, well, since we have a parallelogram, we know that opposite sides are parallel. Okay. And that's useful because I can then do this, where I take this angle and I match it up with that angle. And if I slide this over, parallel lines give me these angles congruent. These are corresponding angles for the parallel lines. So I can say, let me put this back. So angle A is congruent to angle CDE. And that's because parallel lines give us corresponding angles that are congruent. Okay, well then now I know, since A is the same as E and A is the same as CDE, I know that that CDE and E are the same. So CDE is the same as angle E. It's basically saying, well, let me just plug in this E for that A there. So this is going to be substitution. So now I've got that these two angles in my triangle are congruent. And that's useful because that helps me get that these two sides have to be the same. So CD is now congruent to CE. And that's because of the isosceles triangle theorem, where you start with angles and you get sides. So let's see, CD is going to be the same as AB because this thing's a parallelogram right here. So that uses this reason, right? So now I could say CD is the same as AB because parallelograms give me opposite sides that are congruent. And now I've got CD is the same as CE and AB. So I can substitute this guy in right there and say AB is the same as CE. And that's because of substitution again. And that's what we're trying to prove. Okay. Let's take a look at number 3. Okay, show that the diagonals of a rectangle are congruent. All right, so let's see. We've got rectangle ABCD. By the way, the definition of a rectangle is that all 4 angles are congruent to each other. They're all the same size. We want to prove AC is the same as BD. We want to show the diagonals are the same. So AC is congruent to BD. Now, if you look at the proof, down here, we've got triangle ADC and BCD, ADC and BDC, and they overlap. So I'm going to draw them separate right next to this. So there are my 2 triangles that I'm going to look at. Okay, so we'll work our way through the proof here. Let me shrink this down a little bit. All right, now we can fit it all on one page. Okay, so ABCD is a rectangle is given. And the 4 main angles are all congruent. 1, 2, 3, 4. So that's actually the definition of a rectangle, that you have 4 congruent angles. And then that's enough to say that it's a parallelogram. Because remember, one of the ways to get parallelograms is by showing that these 2 angles are the same and those 2 angles are the same, which is true in this case. A is the same as C, B is the same as D. So my reason here is I've got both pairs of opposite angles are the same, so I get a parallelogram. Okay, then the next line, AD is the same as BC. These 2 are the same. Let's see. Well, I know that I have a parallelogram, and I know that if I have a parallelogram, then opposite sides are the same. So we're using this feature. Okay, so let me mark up in the other diagram some of the stuff that we have. Angle D is right here. Angle C is right here. These guys are equal, so that's AD and BC. And then notice there's a reflexive step. Well, notice that this side and this side are exactly the same thing. They're both DC. So I'm going to say DC equals itself, or is congruent to itself. That's reflexive. And now if you think about it, I've got SAS for these 2 triangles. So I can say they're congruent because of SAS. And now that I've got the triangles are congruent, I can match up any parts that I want. Well, let's match up AC and BD. And that's because corresponding parts of congruent triangles are congruent. Okay, so what does this really mean? It actually means that in a rectangle, this and this are the same. But since a rectangle is also a parallelogram, and we know parallelograms cut each other up, the diagonals cut each other, then I know that this and this are the same, and this are the same. But since the whole diagonals, each diagonal is equal to the other one, then really all 4 of these guys are equal to each other. Right? All 4 little chunks of that X have to be the same in a rectangle. Okay? Which comes in handy, because then you got a lot of isosceles triangles in that problem to work with if you're solving for X. You know, doing one of those problems. So let's take a look at 4. 4 says, based on number 3, what can you say about the midpoint of the hypotenuse of a right triangle? Well, let's draw out the same diagram here. And I'm going to draw one diagonal, and then this part I'm going to do dotted lines. Now, if it's a rectangle, I know the angles are all 90 here. And I know that these are all the same now. Right? So start with a rectangle. I'll write out some steps here. Start with rectangle. A rectangle is a parallelogram, right? Which we proved up here, right? Steps 1 through 3. That proves that the rectangle is a parallelogram. So we know that the diagonals have to bisect each other. Right? So AM, let me put letters on here. A, M, C, B, B. So AM is the same as MC, and DM is the same as MB. Since diagonals of a rectangle are congruent, which we proved in number 3, AM has to be the same as MC, has to be the same as DM, has to be the same as MB. So then if we just look at this part, here's a right triangle that's green. Here's the midpoint of the hypotenuse of that triangle. And notice that all 3 of these segments are equal to each other. So at this point, I'm just going to get rid of all of that. Right there. Okay. So if we just look at, just triangle ADC, M is the midpoint of the hypotenuse. And we know AM is the same as MC is the same as DM. Well, a way of phrasing that is the midpoint of the hypotenuse of a right triangle is, and notice, so that midpoint is the same distance from A as it is from C as it is from D. So it's the same distance away from all 3 corners of the triangle. So the midpoint of that hypotenuse is the same distance, equidistant, from the 3 corners, or in geometry, normally you call them vertices, from the 3 vertices. Okay, so this is kind of a useful trick if you're dealing with a right triangle and that midpoint of the hypotenuse. Most people have no trouble remembering, well, if M's the midpoint of the hypotenuse, that these guys are equal. But if it's a right triangle, you can also assume this, and then that creates some isosceles triangles for you to work with. Okay, so let's take a look at 5. So in 5, ABC is a right angle. BM is a median. So median goes from corner to midpoint, which really means M is the midpoint. Okay. Let's see. AB is 15. BC is 8. Find AC, AM, MC, and BM. So basically everything out there. Okay. So let's see. Well, if I look at the big triangle, it's got a right angle here, 8 and 15. One of the sides I need is this one. Whoops. Which is AC, right? Well, AC is the hypotenuse. So if I did 8 squared plus 15 squared, I can get AC squared. So 15 squared plus 8 squared equals AC squared. And if you work this out, you actually end up with AC being the square root of 289, which turns out to be exactly 17. So AC is 17. Okay, so this whole thing's 17, which really means that this part, AM and MC, are each half of 17, right? So AM equals half of 17, which is 8.5. And then MC has to be the same thing, 8.5. So I'll write AM here just so I can put it in its own box. Okay, so now I know 8.5, 8.5. Okay. Well, how about this length right here? So that's actually the point of the previous problem. If you look at the previous problem, we figured out that the midpoint of the hypotenuse of a right triangle, that's M. It's the midpoint of the hypotenuse of a right triangle. It's the same distance away from all three corners. So the distance from M to A is the same as the distance from M to C, should be the same as the distance from M to B. So this is also 8.5. So NB, or BM, also equals 8.5. Okay, and that's it. I hope that helps a little bit, and I'll talk to you guys soon.